The title of this presentation is Reconstruction of Historical Natural Flows and Their Use. Before we proceed, let me first define the natural flows as the flows that would have happened in a river basin had there been no people living in the basin. Why do we need natural flows? The typical use for natural flows is in river basin planning studies. But for planning studies, and the diagram in the bottom shows the difference between what a natural hydrograph looks like and what a regulated hydrograph looks like. This is a bit exaggerated, but you can see that the low flows in regulated systems are a bit higher than natural because we are trying to maintain certain ecological flow targets. And also the high flows, especially during floods, are reduced compared to natural, again because we're trying to keep the flows within the full bank capacity. So what we have on records, most river basins are these regulated flows, while we need natural flows. Now, conducting studies, of course, requires estimates of natural flows, and a typical way of doing this is by running the so-called rainfall runoff models. Those models have to be run through the calibration phase and then validation phase, and this is a typical look of one of the validation phases, where you can see a huge discrepancy between the simulated and observed flows. This is not an exception, this is more like the rule. Here's an example of another study where practitioners who conducted the study had to push the runoff coefficient almost to 1. You can see the value here of 0.996, and in spite of that, the simulated flows, which are represented with the dark lines here, could not reach the observed flows, and we still have a discrepancy of about 2.1 billion cubic meters that builds up in terms of the simulated and observed volume over only a 5-year period. The reason for this, of course, is manifold. We may discuss the quality of data, we may discuss the problems of converting point precipitation to runoff, but in this particular case, it's obvious that we have a lot more flow on the record than rain, and when that happens, there is no way to match any rainfall runoff model. In order to avoid this, in catchments which are gauged, there is a better and more systematic way to reconstruct natural flows. If you look at a catchment with 2 reservoirs, for example, subdivided in 3 subcatchments, the inflow into the most upstream reservoir is calculated on the basis of its outflow and storage levels. We are adding net evaporation here since the reservoir surface area has changed the surface area of the original river. So the inflow into the reservoir can be considered the natural runoff that would have happened if there was no reservoir. Things are a bit more complicated when we go down to the next reservoir, where we have both the effects of intermediate catchment between the 2 reservoirs and the outflow from the upstream reservoir. So the water balance equation is going to include the outflow from the upstream reservoir and local runoff, which you see on the left-hand side of the equation here, and that will be equal to all outflows from the reservoir, plus, of course, volume change and net evaporation. If we are using longer time steps like weekly or 10 daily or half monthly, we can do this on a steady-state basis. If we're using shorter time steps, we have to include the effects of hydrologic routing. Once we do this, there is a way to check whether our calculations are correct or not. And I'm showing you here an example of how it was done in the recent study conducted on the Drina River Basin for one of the storages there. If we run a simulation where we enforce the historical outflows and also the historical water levels, then if our inflows are calculated correctly, we should be getting complete compliance between the historical levels and simulated levels from the very beginning when the dam was commissioned. Once we have this, we can start using this data. The standard practice has been to use the so-called Standard Operating Rule, or SOP, as you see here. The SOP would allow users to use water whenever they need them, but in many instances this would lead to premature emptying of the reservoir. In order to avoid that, this concept of rule curve has been designed, and the rule curve, which is represented here as a dashed line, does not allow the users to lower the reservoir levels below the curve. This prevents disastrous crop failures, but there are additional problems associated with the rule curve because they only work if you manage to refill the reservoir every year. If not, if you end up at a level like this at the beginning of the dry season, then the operator has to improvise. his projected levels can be either like this or somewhere in between. There is currently no easy way to rely on technology, and we're still operating most of our reservoirs based on gut feeling. A possible remedy to this is to use optimization. In this particular case, you're seeing one very simple system with a single reservoir and a single water user. There is initial storage and inflow in the first time step shown. The ending storage is shown as the dashed line. And if we now copy and paste this system to the second time step, the ending storage automatically becomes the starting storage for the next time step. We can extend this system for the entire year. And if we solve the system with additional constraint that the deficits, if we have any deficits, have to be evenly distributed over the year, we're going to get something that looks like optimization of both the rule curve and the demand hedging. In other words, we'll find the best way to optimize both storage and demands. This can be used effectively if you look at possibility of developing perfect reservoir operations for many years. And many years come from the fact that we can also use stochastic hydrology to expand our historical natural flows into much longer series, such that instead of looking at 60 or 70 years of data, we can look at a potential 1,000 years of perfect operating rule. Then we can analyze them statistically. In this particular case, you see about 150 of them plotted on top of each other. If I were to plot all 1,000, you wouldn't be able to see anything. The whole thing would look like an area. But if we now have a situation in the field which corresponds to this particular time interval, and the starting level as of now is 345 meters, for example, then we can select only the solutions which have simulated level which is very close to the current conditions in the field. And all of a sudden we are getting only 35 solutions out of 1,000. And you can see something interesting. They all project almost to the same points over the next 2 weeks. This is a way to create dynamic reservoir rule curves, and it's one way of using optimization, but it is all based on having natural flows as input. The other use of natural flows is for flood management and also for management of hydropower plants. Typically, we have been dealing with floods using simulation models, but the simulation models only solve current time step, and the current time step in many instances has a very short reach downstream of the reservoir. If you assume, for example, 1 meter per second average flow velocity over a cross section, you're going to reach about 85, maybe 100 kilometers downstream of the reservoir, and most river basins are larger than that. The problem is further compounded by the fact that we have to include hydrological routing, such that even if you release steady outflow from the reservoir, this outflow eventually is going through a transformation that looks like this. And what you see is the transformation and further complication by having additional inflows and diversions before you reach the affected area. On top of that, the affected area will have certain full bank flow capacities that we do not want to exceed, and we have to develop some kind of flood damage function to address those, which would look like this. The flood is going to cost us more the higher the flows. This is very similar to optimizing flows through the hydropower plants, except that instead of trying to limit the flow to the full bank capacity, we're trying to limit the flow to the capacity of the turbines. As you can see here, the turbine flow capacity grows with the increase of storage levels. Once it reaches the design level, you typically have to reduce flows because the limitations come from the generator. This technology is based on solving the system for more than 1 day simultaneously while adopting only the solution for the first day. We'd like to solve for the first day by keeping in mind the run-off conditions in day 2 and day 3, which have to come from some kind of forecasting model. It's very important to note that this kind of scheme is not available in any of the simulation models. Here's a very simple system from India where we have 5 reservoirs, and 4 out of those 5 have significant flood storage capacity. In other words, they were designed for managing floods. They also have hydropower, and they also have water users downstream. So the 3,000 and 2,850 figures that you see here are the full bank capacities which we're trying to maintain. This model managed to maintain those full bank capacities in 9 out of 11 historical floods in the period that started in 1961. You can see how the model responds to reservoir levels. In certain instances, if the reservoir is full, it initiates a pre-flood drawdown. In other instances where reservoir wasn't full, the flood storage zone is filled. You can see the comparison of historical with the simulated. Historical ones are shown as dashed dark lines, and they're often more than double compared to the peaks that were managed with the model, assuming only 2 days of runoff forecasts are available. Diagram in the bottom shows you how the quality of the solution changes if we increase the length of the forecast. So for example, for a 1 day lead, we are going to incur some damages downstream, but the 2 day lead is going to bring these damages very close to the limit, the full band capacity, which is 3,000, and here it's about 3,500. And then as you go down to 3 days and 4 days lead, you will have practically no damages. You can see what the model does with storage. In this particular case, we picked one of the storages, although the same is happening simultaneously on practically all storages. The longer the lead, the earlier the drawdown, and the deeper the drawdown. This is basically the way we can summarize. It's time to draw some conclusions and recommendations at the end of this presentation. And the first one would be related to the use and development of natural flows. Engage the river basins with regulated flows, which means in most basins around the world nowadays, estimates of historical natural flows should be developed based on the historical records of storage and flows in the river. The reasons were outlined before, and in our modeling studies, if the input is wrong, the output is also going to be wrong. Secondly, if we are modeling a river basin operation with daily time steps, in particular reservoir operations, we should utilize mathematical optimization and hydrological routing. There are currently only 2 models that can do this. There will likely be more in the future, but simulation models are not the tools that can properly address issues related to proper reservoir operation. When we talk about optimization, obviously you will be able to see a lot of publications these days in various papers about heuristic optimization solvers and all sorts of solvers. They're typically demonstrated on very simple problems, but our modern water resources systems that we are dealing with are not simple. So we should establish some proper benchmarks. They should have reasonable level of difficulty such that models can be properly tested, and they should include issues that we are encountering in practice. And finally, master basin plans should rely on the use of modern optimization technology to improve management of both floods and droughts. We do have a slightly different approach for floods and droughts, as we have identified in this short presentation. You can find out more from additional publications on the website listed in the bottom. If you wish to try the WebBM model, which does all these wonderful combinations of routing and optimization within the optimization framework, you can go to riverbasinmanagement.com and open an account. It's free, it doesn't cost anything. All you need is an email and your own password. Thank you very much for your attention.